Finally, we can move on to part C, Euler's equation of motion, which can be expressed as this equation right here. Now, this notation you might be unfamiliar with. This is called the material derivative. We'll get more into this, but it's used a lot in fluid mechanics. Anyway, where does this equation come from? It comes from Newton's second law, F equals ma. So what we need to do is we need to write out all the forces in one side of the equation and write out mass times acceleration in the other. Now, in fluid mechanics, it's sometimes easier to write mass as an integral of the density. Okay, so this is mass times acceleration. I can write as the derivative of velocity with respect to time, right? And of course, velocity depends on the position and time. And I wrote x as a vector because really this has 3 coordinates. Okay, so this part is mass times acceleration. On the other side, we have to write the forces. One force is going to be the pressure. Okay, now pressure I will write as negative pressure, because we're summing up all the pressure, times the normal vector at a point x. Of course, this is a double integral over the boundary. Why did I write negative? Well, it's because if I have a region omega, the normal vector n usually points outwards. But right now, I want to think about pressure, right? You know, if you think about pressure, usually if you swim down under, you know, if you use a diving board and you swim down the swimming pool, you'll feel like water is pressing in on you. That's why I wrote it as a negative, okay? Because this is pointed inwards. But not only that, we're also affected by gravity, right? And gravity is actually over the region. Density affects gravity, right? Okay, so on the left side, we have gravitational force. We have sum of pressure. Sum of pressure, sum of gravitational force. And so we have F equals ma. Okay, and so by part B, actually, the pressure part can be rewritten as a gradient. Okay, so this is part B, which I showed in the last video. And so I'm going to rewrite this using part B as negative gradient of P. It's the triple derivative integral, right? Plus, be careful about confusing rho and P. Maybe I should write rho in, or maybe I should write pressure in yellow, so that you wouldn't confuse pressure and density rho. Unfortunately, these are the notations used in physics, and we can't really change convention that easily. Oh, I already wrote plus, right? So this part is equal to the triple integral of rho times x and t. So we got this far. Okay, now what do we need to do? We need to derive. We're going to say that acceleration is the derivative of velocity with respect to time. By definition, I mean, that's what we know, right? But notice, position also depends on time. So I'm going to write this as x of t comma t. Now we need to take the chain rule, right? So first of all, we have dv d. Remember, vector x was composed of x, y, and z, right? So this is going to be dv dx and then dx dt plus dv dy dt plus dv dz dt plus just dv dt. This is just chain rule, okay? Chain rule. Now notice that this part can be simplified using a notation. Why? What is dx dt, dy dt, dz dt as a vector? What is this 3×1 vector? It's the change of our position with respect to time, right? So this is actually just velocity. And now, what is dv dx, dv dy, dv dz? Well, this is sort of like the gradient of v, right? If we ignore the time variable. So what do we have here? We have the underlined part is really just the dot product of these two. So the notation, okay, the notation can be viewed as v dot product nabla of v. So imagine the v distributing in here, and we'll get v dot, well, not distributing, the nabla being applied into v, and we'll get our equation right here, right? And we shouldn't forget our partial velocity with respect to time. Okay, so we have, I'm going to rewrite using this underlined portion. So this part was all equal to the derivative of v, right? Which was right here. So now I can rewrite this as the triple integral of rho times, using the material derivative notation, I can write dv dt plus v dot nabla of v. But this is, okay, so on both sides of the equation, I have a triple integral, so maybe I can get rid of it, right? And notice on what we want to prove, we have rho, density, on the denominator, which makes sense because density shouldn't be 0. And so from these two, what color should I use? I'm running out of colors. Maybe I'll use white. From these two being equal, divide everything by rho. I will get negative 1 over rho of the gradient of pressure plus g is equal to dv dt plus the material derivative v dot nabla of v, as desired.